I'll be talking about the development of quantum error correction. So in 1994, I showed that a quantum computer could factor large integers exponentially faster than the best known classical algorithm at the time. And the first, or one of the reactions that I got was, this is never going to work in practice. And why not? Well, Rolf Landauer really explained it very eloquently. We have essentially returned to analog computers as foreseen by Asher Perez in remarkably perceptive comments made in 1985. Analog computers can do far more per step than digital computers, but they cannot take very many steps before the accumulated errors have derailed the computation. So I took this as a challenge to figure out how to protect quantum computers from error correction, and my rebuttal to his objection, well, his objection is essentially that quantum computers are analog, and analog computers can't correct errors. And my rebuttal is that, well, quantum objects are both waves and particles, and quantum computers are both analog and digital. And they correct errors when they're working in their digital incarnation, and they do amazing algorithms because of their analog incarnation. So it's another aspect of this complementarity of quantum mechanics. So, but when I first, Rolf Landauer actually had good reason for making this objection. You can ask, can we use error correction? So in the 1950s, von Neumann showed that you can perform noise-free computations with noisy gates and only a modest amount of extra overhead. And he did this by using massive redundancy. He made many copies of every qubit. And you can ask, can we use classical fault tolerance techniques to make quantum computers error resistant? And at first glance, it appeared that the answer was no. So why not? Well, there's a bunch of quantum theorems, which are really no-go theorems for making quantum computers error resistant. There's the Heisenberg Uncertain Principle, which says you cannot completely measure an unknown quantum state. Basically, any attempt to measure an unknown quantum state inexorably disturbs it. So if you try to measure the error, you're going to disturb the computation, and that derails it. And there's the no-cloning theorem, which says you cannot duplicate an unknown quantum state. Okay, so the simplest classical error correcting code is the repetition code, which is what John von Neumann used to show you can do noise-free computation on noisy classical computers. And what is it? Well, you take every bit in your computer and you replicate it many times. And depending on how noisy the computer is, you may have to replicate it more than 3 times. But I'll use 3 as the example. And now, suppose one of these 3 bits gets corrupted. You can just use the majority to find what it should have been. So what about the quantum version? Well, the obvious quantum version is 0 goes to 3 zeros and 1 goes to 3 ones. So this is a quantum state, which maybe is a spin up or spin down of some particle. And this is 3 particles, which are all spin up. And this is a particle that is spin down, and 3 particles that are all spin down. And I want to say this is not a quantum cloner. So why not? This doesn't violate the no-cloning theorem, because suppose you have a superposition of 0 and 1. So there's this theorem of principle of quantum mechanics that if you can put a quantum system in the state 0 and a quantum system in the state 1, you can put a quantum system in any superposition of 0 and 1. So if you put a quantum system in the superposition of 0 plus 1, and you apply this encoding to it, you get a superposition of 0, 0, 0, and 1, 1, 1, and not 0 plus 1, 0 plus 1, 0 plus 1. And this is what you would have to get if this were a quantum cloner. So it's not a quantum cloner. You can actually do this transformation quantum mechanically, and it's actually can be implemented by a very simple quantum circuit. So how does this work? Well, recall that for the classical repetition code, you just took the majority, and that gave you the answer. And so I want to say this works against a bit flip. A bit flip is this matrix, and it takes a 0 to a 1 and a 1 to a 0. So if you take your quantum code and you apply a bit flip to the second qubit, you get 1, 0, 1 and 0, 1, 0. And these, you can just use the majority to correct them. Well, I think I need to go into more details. So what you do is you measure which bit is different. And there's another simple quantum circuit that will actually make this measurement, which bit is different. And once you measure it, the possible answers are, they're all the same. Bit 1 is different, bit 2 is different, bit 3 is different. And if you know that bit 2 is different, you can apply your Pauli matrix, this is sigma x, to the incorrect bit to correct the error. Yeah. And how do you measure which bit is different? Well, quantum mechanics is a measurement is a projection onto subspaces, and you project it onto one of the 4 spaces, and this subspace is the one where all the bits are the same. This subspace is the one where the first bit is different, the second bit is different, and the third bit is different. And when you know which of the subspaces you projected it on, you then know which bit to correct. And again, you can come up with a simple quantum circuit that performs this measurement. And this, in fact, works for superpositions of encoded zeros and ones. So suppose you have a sigma x error or a bit flip error on the second qubit. That takes you to this state. Now, when you make the measurement, the result is that bit 2 is flipped. And since the measurement gives the same answer for both elements of this superposition, the superposition is not destroyed. And that means that bit 2 can be corrected by applying a bit flip to the second qubit, and you get return to alpha encoded 0 plus beta encoded 1, which is what you wanted. And this was indeed realized by Asher-Perez in his 1985 paper titled Reversible Logic and Quantum Computers. And this is what Rolf Landauer was referring to in the quote that I started the talk with. But in order to do quantum computation, you need to correct more than bit errors. You need to correct phase errors as well. And these keep the quantum computation coherent. If your different elements in your quantum computation lose the relative phases, the computation is not going to work, and you'll get nonsense as a result. And that means you need to protect against phase errors, and phase errors look like this. They take a 0 to a 0, and they take a 1 and apply a minus sign to the element of the superposition containing a 1. So Asher-Perez didn't need to worry about this because what he was trying to do was implement reversible classical computation on a quantum computer. And if you're doing classical computation, you don't need to worry about phase errors. But here, we do need to worry about phase errors. So what happens when you have a phase flip error on this code? Well, an encoded 0 goes to encoded 0. An encoded 1, if you apply a phase flip error to any of these 3 qubits, it takes the whole state to minus the whole state, so it makes a phase flip error on the entire encoded qubit. So what this means is a phase flip on any qubit gives a phase flip on all the encoded qubits. So phase flips are 3 times as likely as they were before you started using this code. So you have a code where you can correct the bit errors but you have phase flip errors are 3 times as likely. So I started thinking about this, and I came up with another qubit code. So what the unitary transformation, this is called the Hadamard transformation, does is it takes bit flip errors to phase flip errors and vice versa. And you can see that by just, doing this computation on 2 by 2 matrices. And so what happens if you apply the Hadamard transformation to the 3 encoding bits and to the encoded qubit? What does this do to our code? Well, it now gives this code, and this takes a 0 to a superposition of all the states with an even number of 1s, and a 1 to the superposition of all the states with an odd number of 1s. So that's the another code. And what happens if you apply a bit flip error to it? Well, if you have a bit flip error on a qubit, a bit flip error on a state with an odd number of 1s takes it to an even number of 1s and vice versa. So a bit flip on any qubit yields a bit flip on the logical qubit. So bit flips are now 3 times as likely. But you can correct phase flips. And I won't go through the details about why this is possible, but since you took a code that corrected bit flips but had made phase flips 3 times as likely, and we apply the transformation that swapped bit flips and phase flips, you can see that a phase flip on the new code should be correctable, while a bit flip on the new code is 3 times as likely. So if you do a phase flip on bit 3, this is orthogonal to all the other bit flips of any bit, or any phase. It's orthogonal to all the other phase flips of any qubit, on either of the code words, and that means you can measure which qubit has a phase flip and then correct that qubit. So, well, have we gotten anywhere? Not really, it looks like, because we have a code that protects bit flips, but now it has made phase flips more likely, but we can also squeeze this code somehow to make it protect phase flips, but now the bit flips are more likely. So what do we do? Well, there's this thing you can do with classical error correcting codes, which is called concatenating them. And this is a very standard procedure in classical error correcting codes, and I've been working at Bell Labs in the same mathematics research group which dealt with error correcting codes. So I'd seen concatenation a lot. And what is it? Well, first you encode the qubit using one of these 2 3-qubit codes. Then you encode each of the other resulting qubits using the other 3-qubit codes. And now this code protects against both phase and bit errors. So how does this work? Well, first you encode using the outer code, which in this case is the one that protects against phase flips, although you could have used the bit flip code first, and now you encode each of the resulting qubits with an inner code. So you take 0, 0, 0, and it becomes 9 zeros, because each of these zeros becomes 3 zeros. And you have this quantum error correcting code, and if you look at it, you can show that it will correct any error in any one of the 9 qubits. And what happens is the outer code corrects the phase errors, and the inner code corrects the bit errors. So, and if you look at it more carefully, it can simultaneously correct 1 phase error and 1 bit error. So it can correct a sigma y matrix, which is just a combination of a sigma x error and a sigma z error. So that was the first quantum error correcting code. So now we can answer the question, how did we get around the Heisenberg Uncertainty Principle? So what we did was we constructed codes where you can measure the error, assuming it falls into some set of likely errors, which in this case are just 1-qubit errors, without measuring the encoded quantum states. And now we've measured the error, we can correct the error without disturbing the encoded quantum state. So that's how quantum error correcting codes work. And this, of course, requires us to find codes where the likely errors are orthogonal to the encoded quantum states. But of course, you can object saying, what about arbitrary errors? I mean, we've shown that we can correct sigma x, sigma z, and sigma y, but there are, infinitely many 2x2 matrices that aren't one of these special 3 Pauli matrices. And you can also measure qubits and do other interesting things to them. So will this code work on those things? And the answer is yes. And there's this wonderful theorem that says if you can fix an error on any of the 3 types of qubits, so the 3 Pauli matrices, fix any of these types of errors, then you can fix any error as long as it's restricted to 1 qubit. And I'm not going to be able to give you the proof, but I can sketch the proof. And basically the idea is that an arbitrary 1-qubit error E can be written as a 2x2 matrix. And any 2x2 matrix, E, can be expressed as a linear combination of the identity and sigma x, sigma y, and sigma z. So now you've done that. You measure the state and you identify the error. And when you identify the error, you collapse the state to be either sigma I, which is no error, or sigma x, sigma y, sigma z, which is a Pauli error. And once you've collapsed the state, well, the measurement will give you the result, which error you've collapsed the state to. So once you collapse the state, you can fix it by applying a single Pauli matrix to the state. Okay, so the repetition code has been known for centuries, if not millennia, but better classical codes weren't discovered until 1950. And why do we need better classical codes? Well, so repetition codes, if you have a very noisy channel, then you need a very long repetition code to correct errors in it. And if you are making errors on this long repetition code by applying noisy gates, then there's some limit to how much noise a 7-bit or qubit repetition code can correct if we're using noisy gates. So that means that there's that means that there are really limitations to repetition codes. Now, Hamming codes, or rather I should say more powerful classical codes, don't have this problem. So the first classical code to be discovered was the 7-bit Hamming code, and it has these 16 code words. And this code maps 4 bits, which is log of 16 base 2, into 7 bits. And it corrects 1 error. So if a linear classical code has minimum weight d, the weight is the number of ones in a code word, then it can correct up to d minus 1 over 2 errors. And you can see this code has a minimum weight of 3 ones in any code word, so it will correct 3 minus 1 over 2, which is 1 error. So this is how the Hamming code works. So you can ask, what happens if you try to adapt the classical Hamming code to a quantum code? And I stared at this for a long time, and Rob Calderbank and I managed to figure it out. And so you can encode 1 qubit into 7 qubits by taking a 0 and encoding it into the superposition of these 8 code words of the classical Hamming code, and a 1 can be encoded into the superposition of these other 8 code words of the classical Hamming code. And this will correct 1-bit error because we started with a classical Hamming code, which will correct 1-bit error, and we just do the same thing on the quantum code to correct the 1-bit error. But why does this correct phase errors? Well, applying this Hadamard gate, which interchanges bit errors and phase errors, to this code yields exactly the same code. So this code also corrects one phase error. And so the quantum Hamming code was discovered independently by Rob Calderbank and by me and by Andrew Steen. And it's the smallest code in the class of CSS codes named after their discoverers. And in fact, CSS codes, once you've found the Hamming code, it's not so hard to generalize it to the class of CSS codes. So what do CSS codes look like? Well, they're based on two Hamming codes, classical error correcting codes, C1 and C2 dual. And we want C2 contained in C1. And the code words correspond to cosets of C2 in C1. And also to cosets of C1 dual in C2 dual. And taking the Hadamard transform switches the roles of C1 and C2 dual and C2 and C1 dual. So because, basically, because if C1 can correct T1 errors, then the CSS code corrects T1 bit errors, and if C2 dual can correct T2 errors, then the CSS code corrects T2 phase errors. So this is just like the Hamming code, except C1 and C2 are more complicated codes. And so suppose we have a better error correcting code that corrects more than one errors. Well, the theorem, which is proved in exactly the same way as the previous theorem, says if you can correct T or fewer errors of the following three types, sigma x, sigma y, and sigma z, then you can fix any error as long as it is restricted to just T qubits. So this means that we can find codes that correct larger numbers of errors. And the proof sketch is just expand the arbitrary T-qubit errors as the sum of those T-qubit errors that we know how to correct, and then the code will correct them. So there's another related question. What about small independent errors on every qubit? Well, what you can do is you can express the small independent errors on each qubit as the sum of the identity of sigma x, sigma y, and sigma z. So these are the three Pauli matrices, or I should say, and now you can expand these errors as a sum of k-qubit Pauli errors, where k is arbitrary, by just applying the distributive law on these independent errors. And what happens when you do that is if these errors are small, then the coefficients on sigma x, sigma y, and sigma z are small in this expansion, and then when you expand it, any term in this expansion that has lots of errors has a very small coefficient on it. So this code will, most of the mass is in errors that have fewer than T qubits, and the error correction code the error correction process will return a state that is very close to the original encoded state. And so that was the CSS codes. And there are still better codes called Five-Qubit Codes. And what happened was that two groups put error correcting codes on the computer. And one group at IBM and one group at Los Alamos. And they discovered this very mysterious looking code. And so I saw their papers, and I tried to figure out what the structure is behind this code, because it obviously has a lot of structure, but it isn't immediately apparent. And actually, this is not the version they discovered. The version they discovered was much less symmetric, but it's equivalent. So I asked Neil Sloan how to compute the symmetry group of this code on computer. And he directed me to the software Magma, and he gave me a sample Magma program where he had computed the symmetry group of another object he was studying. So what did I do? I computed the symmetry group of the code, and it turned out, remarkably, to be exactly the same size as the symmetry group of the object that Neil Sloan was studying, which was actually I want to say it was a Grassmannian packing of spaces in a larger space. I mean, that probably doesn't make any sense, but it was an interesting object that he was studying. And we discovered not only that the symmetry group had the same size, it was exactly the same, and in fact, these Grassmannian packings and error-correcting codes were very closely related objects. And that gave us a clue to find the right description of the 5-qubit code. So what is the right description of the 5-qubit code? So if you know what parity check matrix is in classical codes, the right description is essentially a better, essentially a quantum version of the parity check matrix. So this is sigma x, sigma z, sigma x, tensor sigma z, tensor sigma z, tensor sigma x, tensor the identity on 5 qubits. And what you do is you take these four operations, and you find the class of quantum states that are left unchanged or stabilized by all these 4 operations. And this gives you a stabilizer code. And for a stabilizer code to work, the rows must form a commutative subgroup of the Pali group, and the code words are the quantum states that are not changed by these group elements. So, and if you look at the stabilizer codes, you will realize that the Pali matrices behave exactly like the non-zero elements of the finite field on 4 elements. And the finite field on 4 elements is something which goes into the construction of codes in classical coding theory. So what we discovered was that these quantum stabilizer codes on qubits are exactly equivalent to classical weakly self-dual additive codes over the finite field with 4 elements. And if these are things that classical coding theorists had composed large catalogs of. So now we could just look in these large catalogs and find a ton of quantum codes. So that's how we discovered stabilizer codes. And I should say that CSS codes are also stabilizer codes. And in fact, the Hamming code we talked about earlier, these are the stabilizers. Okay. So now we have quantum codes which can correct errors, but error-correcting codes are really useful when you have a quantum state. You want to encode it, you want to send it over a noisy channel, and you want the other person to decode it. But in this process, you assume that the operations that the sender is receiving are fault-free quantum operations, and the operations the receiver is doing are also fault-free quantum operations. But what we really want to do is use quantum error-correcting codes to protect the information in our quantum programs. And our quantum programs The gates are all noisy. I mean, the gates in the encoding processors are going to be noisy. The gates in the decoding processes are going to be noisy. And the gates in the, I accidentally moved ahead. And the gates in the, and the gates in between doing the computation are also noisy. So what you need to do is you need to implement gates on encoding qubits without decoding them. Because if you have two encoded qubits and you decode them, perform an operation, and re-encode them, when you're performing the operation, you are exposing the qubits to noise, and once you expose the qubit to noise, your quantum computation is not going to last very long. So you need quantum fault-tolerant circuits. Now this was the quantum fault-tolerant circuit that von Neumann used. If you want to do an AND on two encoded qubits, so these are just the repetition code, what you do is you do a bitwise AND on each of the, on the ith qubit of each of them. And now if you have relatively few errors in the input, so here you have one error right here, and you make relatively few errors in your computation. So here you've introduced another error. Then when you take the majority of these, you still get relatively few errors, and maybe you don't take the majority perfectly. Maybe you have a gate in here that screws up and you only get 4 ones and a 0. But most of the time, you will, this operation will give you fewer errors than you started with. So this, when you can prove that this will do, will let you do a lot of computation before you happen to get more errors than your code can handle. So we want to do exactly the same thing for quantum error correcting codes. So how do we do this? Well, we need circuits that implement quantum gates on encoded qubits without decoding them. And what I'm going to talk about now is transversal gates. So you can suppose you can implement a quantum gate G by applying the gate G to each qubit of the code, and that applies the gate G to the encoded qubits. So if you apply, so here in this circuit, we're applying a C0 gate, which is a kind of quantum gate, to each of the, to the ith qubit of the first encoded qubit and the ith qubit of the second encoded qubit. And what this does is it implies a C0 gate to the entire, to the two encoded qubits. And transversal gates are automatically fault-tolerant because suppose you have an error in the third qubits. Well, it can never spread to any of the other qubits because the third qubits of this code are only interacting with the third qubit of this code, and it's not going to spread to the first qubit. So transversal gates are automatically fault-tolerant. And you can apply any gate in the Clifford group fault-tolerantly by using transversal gates. The Clifford group is a group of quantum operations which is very useful, but gates that are not, to do quantum computations that really improve over classical computation, you need to show that you can do gates not in the Clifford group. And these are performed by something, or I should say, in the most popular quantum fault-tolerant methods, these are performed by something called magic states. So a magic state is something that looks like this, an encoded 0 plus the square root of I times an encoded 1. And if you have a quantum magic state, you can use it to perform a gate that's not in the Clifford group. And if you have a lot, the other nice thing about magic states is if you have a lot of imperfect magic states, you can distill them with even noisy operations and get fewer magic states that are all much more perfect than these imperfect ones. So what you do is you take 16 magic states which have, say, 5% error, and you use this wonderful circuit that people have discovered, and you get one magic state that has 1% error. And so this gives you magic states that are good enough to use for quantum computation. So of course, this distillation process takes a lot of imperfect magic states and yields only a few really good magic states after you've done this. I mean, you may have to do this twice if you want your, if you start with noisy magic states, you do it once and you get down from, say, 10% to 1%, and then you do it again, you get it down from 1% to 0.001% error, and that may be good enough for your quantum computation. So the current design for factoring circuits, in fact, current design for any large quantum computation which is fault tolerant, use a large fraction of the chip error for something called magic state factories, which produce a lot of magic states, and these magic states are fed into your computation, and then they make your computation fault tolerant. So this is really one of the reasons that if you want to do, so suppose you want to do a computation that has 2,000 logical qubits. I think the best estimates right now is that you're going to need 1 million physical qubits to implement these 2,000 logical qubits. And part of that is because you need to do magic state factories, and the other part is that these quantum error correcting codes, if you want them to be good, take up a lot of, you need to use a lot of qubits to encode each logical qubit. And there's something that's called the threshold theorem, which is if all your gates have an inaccuracy below some threshold, epsilon, say 10 to the minus fifth, then you can add a moderate amount of overhead. Well, I don't know if moderate is the right word. I mean, you're going to expand the number of qubits you need by 1,000 and the number of gates you need by a similar factor. But you can use a moderate amount of overhead to do computations with arbitrarily small probability of epsilon with overhead polynomial log 1 over epsilon. And of course, if your gates have inaccuracy below 10 to the minus seventh, then the overhead is much less than if they have inaccuracy 10 to the minus 5. So I showed that you could do n steps of quantum computation if your gates had error at most 1 minus 1 over log n. And a number of groups of people, including Aharonov and Ben Orr, improved this theorem to tolerance 10 to the minus sixth. And of course, this threshold has been proved since. If you want a reasonable amount of overhead, 10 to the minus 5 is a good accuracy to aim for. 10 to the minus 4 has more overhead. If your gates are inaccurate in 1 part in 100, this theorem still holds, but the amount of overhead is absolutely astronomical. I mean, it's only a fixed amount, but it's really huge. Okay. And the trick I needed for the last step that I didn't think of, again used concatenated codes, the same trick I'd used to do the repetition code, but I didn't think of it this time. Okay, so how much more time do I have?
I think we can another 15 minutes. For sure.
Okay, so what I'm going to do now is just, go lightning fast, or go fairly fast through a number of improvements on the error correcting codes I've discussed already. So Alexei Kitaev discovered a completely different way to achieve fault tolerance. So what you do is you take a grid with qubits on the edges. So you have your qubits in this array, and you make a row of the parity check matrix for each vertex and for every face, as in this picture. So what you do is your parity checks are these 4 sigma z's around this face and the 4 sigma x's around every vertex. And this is a code, if you have put the right boundaries on this thing, it's a code that encodes 1 qubit. And the minimum distance of this code is the side length of this code. So for example, this code I think has minimum distance 3, which means it would be able to correct 1 error. But if you had a 15 by 15 grid, it would have minimum distance 7, which means it would correct, it would have minimum distance 15, which means it could correct 7 errors, which is, pretty good. And this Toric code is in fact a CSS code. And if you have a Z error if you have errors that pass all parity checks, so for example, this Z error, it must commute with all the X parity checks. So this means that there must be an even number of Z's at each vertex, and we can decompose it into paths. And if the paths consist of loops, then after we correct it, it can be covered by squares, and that means that the state that it encodes is the same as the state without an error. So it's not actually an error. So if you have an error on these 8 edges, it would not be an error. If you have an error which is, which has a Z which ends at a vertex and doesn't have any other Z's, then you can detect it, and then you can guess which state is an error and or what the actual error is, and probably correct it. And the errors you cannot correct are the ones that are paths that wrap around this code. Like here. This is an error you cannot correct. But, if you have, if you have a 3 by 3 cube grid, then the paths. So what we're going to do is we're going to assume that these qubits down here are connected to the qubits up there, because it's much easier to think about this, although it's not really necessary. And now the uncorrectable errors are ones that wrap all the way around, and they need to have a reasonable number of Z errors on a reasonable number of qubits. So these are very unlikely. So this is how Kitaev's Toric code works. And generalizing this, you get surface codes, and you can remove parity checks from the grids and have surface codes which just connect qubits that are adjacent to each other, and you don't need this wraparound. And one of the reasons surface codes are so, a lot of designs for quantum error correcting, for computers with quantum error correction use surface codes. And the reason they use this is that, the superconducting qubits are laid out on a chip, and they only interact with qubits close to each other. And surface codes, also have this property that you can lay them out on a plane and only interact qubits that are closer to each other and correct errors. So surface codes are well suited for quantum computers with planar layout, which is superconducting quantum computers. Okay. So now what I want to do is go quickly through more recent developments in quantum codes. So there are hypergraph product codes, which were discovered in 2014. And these were the first codes to have longer than order of log n minimum distance. And they have order of root n minimum distance, which is pretty good. And like CSS codes, they're constructed by combining two classical codes, but they are combined in a completely different way. And if you combine two repetition codes represented by parity checks between adjacent qubits, so you have a repetition code, you want this to be either 0, 0, 0, 0, 0 or 1, 1, 1, 1, 1. Well, what you can do is you can check that any two adjacent qubits have the same value, and that means that the only possible values of these qubits which pass all the parity checks are 0, 0, 0, 0, 0 or 1, 1, 1, 1, 1. And I'm also going to put a link between the first and the last bit here. And so you take this one, and now you combine it with this repetition code. What you get is you get Kitaev's Toric Code, where this wraps around and this wraps around. And you can also, there's other ways of finding parity checks for the repetition code. You can just, do a check between two adjacent qubits and not wrap around. And when you do that and combine them, you get Kitaev's surface code, which is planar and where the grid doesn't wrap around. And so there's lots and lots of ways to combine two different codes to get a hypergraph product code. And if you do this wrong, the hypergraph product code only encodes 0 qubits, which isn't a very useful code. But if you do it right, it will encode 1 qubit, which is, the minimum number of qubits that useful code will do. And now there's also something called Floquet Codes, and I don't have time to really explain them, but they don't encode a fixed subspace. They encode a subspace that changes. What you do is to do a step of error correction, you measure some relation between two of your qubits, and then the encoded subspace changes with this step. And this is really very much harder to think about, but it actually will let you save a lot on the number of gates needed to do quantum error correction. Because, Floquet codes, so this Toric code, Kitaev's code, you needed to measure four qubits to do a parity check. You can do exactly the same, you can do essentially the same thing with a Floquet code and only measure 2 qubits at each step. And that's much more useful because if you measure 2 qubits and you have noisy gates, then it's much less likely you'll get an error than if you measure 4 qubits at every step. So these were only discovered in the last 2 or 3 years, and there's still a lot of research going on in them. And then the other more recent thing is LDPC codes, and these codes have a minimum distance which is proportional to the number of qubits they use to encode things. So this is, these are what was called good codes in classical coding theory, and the construction of these codes uses hypergraph product codes. And they prove something called NLTS conjecture, which is that there were no low energy states in the code. So if this so this solves an. So quantum PCPs are probabilistically checkable proofs, and they're an amazing construction in classical computer science. And people for the last 20 years have been trying to get quantum PCPs. And the NLTS conjecture of Hastings showed that they're, if it had been false, then it would have shown that quantum PCPs were impossible. But it's true, so maybe quantum PCPs are possible, but we don't know yet. Okay, and so I think thank you. That's end of my talk.